In our first submodule, for Module 5, we'll look at linear models. So what's the basic idea here? We want to use linear models when the rate of change of the quantities we're looking at are constant. These are somehow the most simple models. You'll see the functions we use to represent them are just degree 1 polynomial or linear functions. In comparison, look at exponential models. These will be characterized by having a constant rate of doubling or doubling, etc. In trigonometric models, we'll look at phenomena that are periodic over time. But we'll start with linear models because they're the most straightforward. So recall that our linear equations are of the form y equals ax plus b, where a is the slope, or in the context of our model, the rate of change. So the slope you can think of as like geometric. When I plot this function in the plane, the slope will tell me, what direction is it moving in and how steeply. But as soon as I start applying this to a real problem, I just want to think of that in terms of slope. I want that number represents in the real quantities I'm discussing. So I want to think about that as the rate of change of whatever quantities I'm measuring. So the rate of growth is typically application dependent. By which I mean, depending on what physical scenario we're modeling, you might come up with a different interpretation for the coefficient a. And I'll remark that, in general, we think of this number b as the y-intercept. But in the context of models, b can also be thought of as like your starting point. That is, when I let x equal 0, my output is just b. So if I think of 0 as somehow the start or the original value, b is what you output at the start. So of course, with these types of problems, it's fairly straightforward to compute values of x given y and vice versa. So these types of linear equations are especially nice because if I have a physical system that's modeled by a linear equation, I can easily plug in my inputs and get the outputs, but it's also very easy to set an output and determine what the input is because it's just a linear equation. So it just involves very simple algebraics. So let's look at a simple example. So you might encounter this type of question on the CLEP. Suppose it costs $20 to manufacture a widget with a startup cost of $1,000. So first of all, what are widgets? Well, widgets are commonly used in economics to describe a generic product. They don't really have any real meaning. They're just used to say, well, suppose it was any old product. I don't care if it's teddy bears, automobiles, or anything. Just a generic product is given the name widget. So this on don't worry about what it is. It's just a general concept for these types of things. But I'm telling you how to compute how much it costs to make them. It costs $1,000 at the start to make any number of them, and then for each widget I make, it'll cost an additional $20. And our question is, what is the cost function in terms of the number of widgets manufactured? So in this case, my input to the function should be number of widgets, and my output should be total cost. So I'll write C of W to say input W, the number of widgets, and output the cost. So how would we do this? Well, I claim that this is a linear model. Why do I know that? It tells me that I have a fixed rate of change, that for each additional widget I produce, My cost is simply an additional $20. In general, production doesn't work like this. The more things you produce, in many cases, it gets easier to produce new things. You get what's called an economy of scale, where it's actually easier to produce, say, the 10,000th item than it was to produce the first item, because you've the necessary infrastructure. In this case, that's not happening. It's saying the cost of making a new widget is always the same. It's $20 per widget. Now, I do have an additional cost I have to incorporate here, which is also given in the statement of the problem. It costs $1,000 at the start, any widgets. So if I want to make one widget, I have to pay $1,000 at the start plus the $20 for the one widget. If I want to make 10,000 widgets, I pay $1,000 at the start and then $20 for each of the 10,000 widgets. So I have to add in 1,000 here. And this is my model. So we can interpret this as 20 is equal to the slope of this line, or the rate of change, and 1,000 is equal to the y-intercept, or starting value. So I can plot this, or I could plug in for different values. So if I asked, for example, how much to make 100 widgets, I would simply plug in C of 100 and get something like, I think, 21,000. Right? 1,000 to start and then 20,000 to make each widget. And so another question I could ask, how many widgets can I make with, say, $10,000? Well, I would just be solving 10,000 equals C of W. And this would not be difficult, because it's simply an algebraic equation. So what can we tell about this type of linear model? Well, we can tell that at the beginning I have to pay this steep cost. So it's really not benefit to make a small number of widgets, because I only have to pay that cost once. If I want to make one widget, it costs me $1,020. So it doesn't make sense just to make one. I should make more and more and more. So for these types of problems on the CLEP, you want to be able to interpret the slope and the y-intercept, and also be able to solve simple problems, ones I've shown you here. Given the verbal description of the model, write the equation for it, and then be able to solve simple problems like, what is the cost and how much can I make given an amount to spend on the cost?